I want you to try a little thought experiment with me. It might feel a bit uncomfortable, but just stay with me for a second.
Okay, I'm with you.
Imagine you wake up tomorrow morning, you roll over, you grab your phone, and nothing.
No bars.
No bars, no Wi-Fi icon, just that little disconnected symbol just sort of staring back at you.
The dreaded dead zone. Yeah, we've all been there.
But what if it's not just a dead zone? What if it's
Yeah.
everywhere? You go to your living room, your smart thermostat is just flashing this angry red error code.
So no heat.
No heat. You try to turn on the news. The streaming service just spins and spins. You can't email your boss to say, hey, I'm offline.
You can't even text anyone to see if they're having the same problem.
Exactly. You can't tap your watch to pay for coffee. Life as we know it basically grinds to a halt. We're living inside this invisible nervous system that we barely understand.
That is a fantastic way to frame it. A nervous system. It carries all the signals that keep the body, or in this case, our whole society functioning.
And you don't notice it until it's gone.
You really don't. Not until a nerve gets pinched.
And today, we are going to perform a little digital surgery. We're dissecting that nervous system.
I like it.
We're doing a deep dive into a presentation by Dr. Nima Zahadat called Introduction to Networks and Network Terminology. And our mission today is to get past the, unplug it and plug it back in level of understanding.
Which, to be fair, does solve about 50% of problems.
It really does. But we want to know why. We want to understand how a message actually gets from A to B. And this is a big one for me, why people keep mixing up the internet and the web.
Oh, that's a classic. That trips up almost everyone, even some people in tech. But before we get there, we should probably start with a basic definition. What even is a network?
Right. It's just a bunch of blinking boxes and cables.
Well, at its core, Dr. Zahadat defines it as simply a collection of computers and devices connected to shared data and resources. But the key part is that connection can be physical.
The hardware.
The hardware, the cables, the routers. Or it can be logical.
Okay, logical. Physical, like I can trip over a cable. What's a logical connection?
Think of it like language. You and I could be in the same room physically connected, but if you only speak French and I only speak Japanese, we're not really connected, are we?
No, not at all.
The logical connection is the protocols, the software, the rules that let devices actually understand each other.
So the physical is the wire, and the logical is the grammar.
Perfectly put. And to understand that grammar, we have to look at the history, which I think is where the source material really gets surprising.
Yeah, I thought the same. We all think the internet started, what, in the 90s?
Maybe the late 80s if you're being generous. But the notes trace it back way further, to the telegraph.
The telegraph. That feels like ancient history.
It is, but think about the function. It was the first time we encoded a message, dots and dashes, and sent it over a wire to be decoded. That basic concept is the great-grandfather of all of this.
Okay, I see the thread, and then the telephone adds voice. But the real leap, the thing that gave birth to the internet, sounds like something from a spy movie.
ARPANET.
ARPANET, the Advanced Research Projects Agency Network, funded by the Department of Defense, late 60s.
So this was a military project.
Absolutely. And you have to understand the context. This was the height of the Cold War. They were terrified of a nuclear attack wiping out their communications.
Because the old phone system was centralized, right? You take out one switchboard, you take out the whole city.
Exactly. That's called circuit switching. An operator literally plugs in a wire to create one dedicated circuit. If that line gets cut, the call is dead. ARPANET introduced something totally new, packet switching.
Okay, this is a term I hear all the time. Break that down for us.
Okay, imagine you need to send a very long book to a friend. In the old way, you'd hire one truck, put the whole book in it, and send it down one specific highway, if that highway is closed.
The book's not getting there. Right. In packet switching, you rip every single page out of the book. You put each page in its own envelope, address it, and just toss them all into the mail system.
That sounds incredibly chaotic.
It is, but it's resilient. Page 1 might go by truck. Page 2 might fly. Page 3 might go by train. If one road is blocked, the other pages still get through using different routes. They all arrive, maybe out of order, but they get reassembled at the end.
So the tech we use for watching cat videos started as a way to survive nuclear war.
That's pretty much it. The internet is fundamentally built to survive. And the protocols they developed for ARPANET, specifically TCP/IP, are still the bedrock of everything we do today.
Let's double-click on that alphabet soup, TCP/IP. The source uses a really good analogy here, the Postal Service.
I love this analogy. It makes something abstract so tangible. So TCP/IP is Transmission Control Protocol, Internet Protocol.
It's a mouthful.
It is, but just think of it as the rules for that envelope system. First, you have your data, your email, or whatever. TCP is the part that breaks it down into those little packets. It handles the packing.
So TCP is the packer.
Right. Then you need to write an address on the front of the envelope. That's the IP Internet Protocol. It puts the destination on the packet.
And then you drop it in the mail.
And the network starts routing. But here's the magic of TCP, the part that makes it so reliable. Confirmation.
Like a return receipt.
Exactly. The receiving computer has to send a message back saying, hey, I got packet number 45. If the sender doesn't get that message, it just assumes it got lost and sends that one packet again.
Wow. So every time I load a web page, there's this invisible conversation happening. Did you get that? Yes. Did you get the next one? No. Okay, sending again.
Millions of times a second. That handshake is what guarantees end-to-end communication. Without it, it would all just be noise.
It really is an engineering marvel. So we have the rules of the road, TCP/IP. Let's talk about the map. The notes mention LANs and WANs.
Right. LAN is local area network. The key word is local. Your house, your office, high speed, low latency. The tech there is usually Ethernet.
The cable with a little plastic clip that always breaks.
That's the one. Or Wi-Fi, which is basically wireless Ethernet. But when you need to send that data to another country, you leave the LAN and enter the WAN.
Wide area network.
Correct. The WAN connects all the different LANs together, and it uses different, more heavy-duty technologies. And there's a really critical distinction the source makes about LANs.
What's that?
They don't understand content. They're just transport. Think of a long-haul trucker. They don't know or care if their container is full of bananas or TVs. Their job is just to get the container from A to B.
So the WAN is payload agnostic. It just sees packets and destinations.
Exactly. And to manage all that traffic, every device needs an identity. This is where we get into M addresses versus IP addresses.
Yeah, this always confused me. Why do we need two different kinds of addresses?
It's the difference between who you are and where you are. A MAC address is like your fingerprint. It's a unique number burned into the hardware at the factory. It never changes.
Okay, so it identifies the device itself.
The specific device. But your fingerprint doesn't tell me where you live. That's the IP address. It's like your postal address. And crucially, it's hierarchical.
What do you mean by hierarchical?
It's organized in layers. You couldn't run a global postal service if every house just had a unique name, like the Blue House. It wouldn't scale.
You'd never find it in there.
It would be chaos. So we have states, cities, zip codes, street names. That's hierarchy. An IP address works the same way. The first part tells the routers which country, the next which network, and so on, until it finds your specific device.
That hierarchy is what makes the whole system work on a global scale.
Precisely. And that also helps explain the difference between two pieces of hardware, switches and routers.
Right, which my box at home seems to do both.
It does. It's a combo device, but they're different jobs. A switch is a local traffic cop. It works inside your LAN using MC addresses to send data between your computer and your printer. It doesn't know about the outside world.
And the router?
The router is the diplomat. It stands at the gateway of your network and talks to the outside world. It uses IP addresses to route traffic between different networks. It's the only thing that knows how to get to the internet.
Okay, that clears things up. Now, let's tackle the big one. Internet versus the World Wide Web.
The classic confusion.
I feel like 99% of people use them interchangeably. Going on the internet means opening a browser.
And technically, they're wrong. It's like confusing the roads with the cars driving on them.
So set the record straight for us.
The internet is the infrastructure. It's the global system of connected networks. The physical cables, the routers, the TCP/IP protocol. It's the plumbing.
And the web?
The World Wide Web is just one application that runs on top of that plumbing. It was invented by Tim Berners-Lee in 1989. It uses things like web browsers and protocols like HTTP.
So what's an example of using the internet without using the web?
Email, or online gaming, or an app on your phone that unlocks your car. All of that uses the internet, but you're not on the web.
That's a huge distinction. And to use the web, we use names, like google.com. But computers use numbers.
Right, and that's where DNS comes in, the domain name system. It's basically the phone book of the internet. You ask for a name, it looks up the IP address number so the computers can connect.
So if DNS goes down, the whole thing feels broken.
It feels broken, but the lines are still there. You just lost the phone book.
Okay, moving up the ladder of complexity. The cloud. The source grounds this in a very specific concept, virtualization.
Yes, you cannot understand the cloud without understanding virtualization. Traditionally, one physical computer ran one operating system.
Which is inefficient, right? You might only be using 5% of its power.
Exactly. So virtualization uses software called a hypervisor to slice that one physical server into multiple virtual computers.
A computer inside a computer.
You got it. You can run a Windows machine and a Linux machine on the same physical box, totally isolated from each other.
Like an apartment building. One structure, many different tenants in locked units.
That is the perfect analogy. Now take that apartment building and scale it up to the size of a city. That's the cloud. When you save a file to the cloud, you're just renting a tiny apartment in a massive data center somewhere.
The complexity is abstracted away.
That's the history of computing in a nutshell. Hiding complexity. But as we make things easier, we often make them more vulnerable.
Which brings us to wireless and the Internet of Things, or IoT.
And this is where the security expert in me starts to get a little nervous.
Let's start with Wi-Fi versus Bluetooth.
Sure. Wi-Fi is pretty robust. It supports the full TCP/IP suite, and modern versions are quite secure if you have a strong password. Bluetooth is more for short-range things, headphones, smartwatches. It's inherently less secure.
And now we have the IoT explosion.
Yeah.
My fridge, my doorbell, my toaster are all on the network.
And this is the problem. A laptop gets regular security updates. Your $20 smart poster probably has a default password you can't even change and will never get an update.
So I'm putting a steel deadbolt on my front door, my firewall, but I'm leaving the bathroom window wide open with a cheap smart bolt.
That's exactly it. You're expanding what we call the attack surface. An attacker gets in through the toaster, and now they're inside your network. They can bypass the firewall from the inside.
That's terrifying. Which leads us to security and risk management. The source says security isn't just a product you can buy.
No, you can't just plug in a security box and call it a day. It's a process. It's about policy. And it's about people. The best encryption in the world doesn't help if someone writes their password on a sticky note.
The notes mention auditing a lot.
Because the threats change every single day. An audit is where you're constantly checking. Are our defenses still working? Is that toaster still secure? If you're not auditing, you're just guessing that you're safe.
And when the guess is wrong, you need a disaster recovery plan, do or die.
A plan for when it all hits the fan. But here's the key takeaway from Dr. Zahadat. A DR plan is useless if it hasn't been practiced.
You mean like a fire drill?
Exactly like a fire drill. I've seen companies back up their data every night, feel totally safe. Then they get hit by ransomware and they find out the backups have been corrupted for 6 months.
Oof, that's a nightmare.
If you haven't tested the lifeboat, don't assume it floats.
That is sage advice. Now, before we go, I want to touch on something that feels very forward-looking. Artificial intelligence.
The new frontier.
We've been talking about the pipes, the network,
Yeah.
but now we have AI. Entities on the network that can write code, make their own decisions.
It changes the whole game. Until now, humans created the traffic. Now machines are creating the traffic.
And the source raises some serious ethical concerns. If an AI optimizes traffic, but blocks an ambulance because it decided the route was inefficient, who's responsible?
Or in healthcare. An AI making a diagnosis based on data sent over these networks. Can we trust it? We're layering this incredibly complex autonomous brain on top of the infrastructure we've just been discussing.
It all comes back to that idea of complexity. The layers are getting so deep that almost no single person understands the whole stack anymore.
Which is why understanding these fundamentals is so important.
So a quick recap. We went from the telegraph to the packet switch resilience of ARPANET to the Postal Service rules of TCP/IP.
We clarified that the web is an app on the internet, the cloud is a city of virtual machines, and a switch is a cop while a router is a diplomat.
We ended on the risks of plugging our toasters into this global nervous system and why you have to practice your disaster plan.
It's a lot, but it's the foundation of modern life.
And here's the thought I want to leave you with. We are rushing to connect everything, building this sort of digital superorganism.
A planetary nervous system.
Exactly. But we learned today that system is surprisingly fragile. It needs constant defense. So as we hand more control to AI and connect more insecure devices to our homes, here's the question. Are we building a brain that's too smart for the nervous system it lives in? Are we prioritizing convenience over stability and creating a system that's just destined for a massive nervous breakdown?
That is a question that is definitely going to stick with me.
Me too. Thanks for listening to this deep dive. Hopefully, next time you see that Wi-Fi icon, you'll have a little more appreciation for the miracle behind it.
Stay connected, everyone.